5. Choose your own adventure, Slinky Drop. So in this lab, the purpose is to examine how a spring behaves when stretched and released, focusing on whether it collapses immediately or only after reaching its relaxed length. This behavior is explained using Newton's second law, which is known as the momentum principle. And a little preview of the results is that in the lab, the bottom of the slinky remains stationary until the top of the slinky catches up to it. Now, when looking at the fundamentals of this law, we're basically focusing on Newton's second law / the momentum principle, which states that the net force equals the change in momentum divided by the change in time. And then the definition, as stated before, is that the change in momentum indicates movement changes within the system and surroundings. Now, a procedure for this lab is that first we're going to download the video of a fallen slinky and upload it to the tracking software. Then we're going to use the center of mass calibration stick and coordinate the axis on tracker to accurately record the slinky's fall data from frame by frame. We are then going to develop a computational model to demonstrate that the bottom of the spring remains stationary until the top reaches it. Then we're going to compare the computational model to the tracker data, analyzing the connection to Newton's second law. So then here's just a screenshot of the tracker and the video used. And then the observations at the start time was 0 seconds, the end time was 0.767 seconds, the velocity in the beginning was 0, and its initial position was 0. And we consider the system the slinky and then the surroundings Earth, which means that gravity is acting on the system of the slinky. Now here's some examples of the computational model. And then a comparison between the tracker versus the computational model. Now, some sources of error could include human error when using the tracker, which includes incorrect placing of the center of mass and in the video, and there's no effective air drag on the falling object in the tracker model, which is in the computational model, which is different than the tracker model. But as shown in both models, they're mostly similar, and the differences are slight at best. So to conclude this experiment, Newton's second law of the momentum principle is seen in the video model through the object's acceleration, mass, and force. As mass increases, force increases, and the same happens with acceleration. The experiment showed that the bottom of the slinky only starts to move after its relaxed length. And this has showed that when you drop a stretched slinky, the top collapses due to gravity, but the bottom doesn't move immediately because the tension force from the stretch coils above and is still pulling up on the bottom. But when the slinky reaches its relaxed length, the tension is gone and the net force becomes non-zero and it's just gravity. And the bottom starts accelerating down, which is shown. The computational model, which includes gravity and drag, is almost exactly the same as the slinky's movement in the experimental video. Thank you.